So now we're in chapter 4, exponential and logarithmic functions. And we're going to be starting with section 4.1, which is exponential functions. For this chapter, you really want to have a scientific calculator that allows you to do the things that we're going to be doing that I'll talk about over the course. This is the one that I recommend. But having one is imperative, just because a lot of students will say, oh, I'll just use my calculator, it'll be fine. But in reality, there comes a point where having the knowledge of just a basic scientific calculator for this course and trigonometry and beyond, calculus and such, is very, very useful. And the more you practice, the better off you're going to be. So please have a scientific calculator to use during this chapter. And let's begin. So section 4.1, like I said, is exponential functions. And what you're seeing here is just a basic example of an exponential function. So notice that what we have here is the base of the exponential. In this case, the base is 2. And I want you to notice that the exponent is the variable. The exponent is x. And so this is really important because it makes it very different from, say, an x squared. So x squared is very different than 2 to the x. And that's how I would read this example right here, would be 2 to the x, as x is the exponent. So we'll take a look at what graphs of exponential functions look like, and they all follow a basic shape, which is important to kind of remember. But what happens is, as you can see, is just like any situation, if we plug in values to our function, we would have, a situation like this, 2 to the negative 2. We'd want to remember our exponent rules, that that's 1 over 2 squared, or 1/4. And so that would be our y value, negative 2 comma 1/4. So if I put that onto my graph, it's just going to be a little point right there. It's the best I can do. There we go. And we would just continue on. F to the negative 1 is going to be 2 to the negative 1, or 1/2. 1 over 2 to the 1. So 1/2. So that's bigger. So we're going to go up a little bit, halfway. And if you want, you can pause, see if you can get the other values here. That's, an important thing to be able to do. And we get 1. And then once we start putting in positive values, not surprisingly, 2 to the 1 is 2, and 2 squared is 4. So we're going to have 1, 2, and 2, 4. So what we really want to see is that the shape of this is not linear. This is not a linear function. So your line should not be super straight. This is a function that curves. So we're going to curve it up, and we're also going to curve it the other way. This is what would happen if we found more function values. It would go up, and then it would approach 0. That's what's happening over on the left-hand side of our graph. So some other examples. So exponential functions always have that exponent that's x. In the last example, we had 2 to the x. We could have something like 1/2 to the x. The base does not have to be a whole number. We could have, a different value. Just obviously doesn't have to be 2. We have a base here of 3. It's totally valid. We could have something, it doesn't have to be, like I said, a whole number. You could have something like 4.3 to the x. It's fine. Obviously, in situations like that, you'd really want to be using your calculator for the values. Let's see what else I can do here. F of x, we could have, just some random decimal there. Those are all examples of exponential functions. Notice that the common theme there is that x is always the exponent. And there's some properties of them. So I'll go back to my other example, my graph that I made, so that you can be reminded. So take a look at the first two here. So when you have a exponential, that is a to the x, where a is, some real number. The domain is all real numbers. So we go all around from negative infinity to infinity, our domain. The range, notice all positive real numbers. So we can see that pretty easily here that we are above the x-axis and going up, but we are also crossing all of our x values. We have a y-intercept that's 0, 1, and that's because anytime you put 0 in for x, as you can see, for all those examples at the top, if you put in 0 for x, anything to the power of 0 is 1. Except we don't do 0 to the 0, but any other value to the 0 is 1. There's no x-intercept, so again, you can see that pretty easily here. You can see that y-intercept of 0, 1. You can see that there is no x-intercept. We do have a horizontal asymptote at y equals 0, so you can see that right here. This is, of course, y equals 0. And that's simply because if I put in larger and larger negative values, 2 to the negative 10, 2 to the negative 20, 2 to the negative 100, that's going to be 1 over 2 to the 10th, 1 over 2 to the 20th, 1 over 2 to the 100th. Those are increasingly small numbers, but they are still small numbers. They are still positive small numbers. So they're getting closer and closer to 0, but they're not ever touching 0. There is no value for x that you could put in, and you're going to get 0. So 0 is never a y value, which means that we have a horizontal asymptote at the line y equals 0, because it gets very close to that. You will see that depending on what your a is, that the function may be increasing or decreasing. Okay, so this, there we go. This is an example of an increasing function because the base is 2. So when the base is greater than 1, as you can see, you're starting to put in larger and larger values of x, so your y value is getting larger and larger, so that function's just going to increase. Now, if you had instead a being between 0 and 1, so something like this example of 1/2 to the x, what's going to happen is it's going to kind of flip it. So if a is between 0 and 1, so this is case number 6 here, the function's going to be decreasing. So it's actually going to start high and then go low. So I will just do a quick showing you here that it would do something instead like this. So it's still going to come through 0, 1. Sorry, I was just trying to make that happen the best I could. And it's going to decrease as x gets bigger. So if a is between a fraction, decimal, something between 0 and 1, that's what it's going to look like. So just so you have that as a visual there, just for you, so you can see it. And then the last thing is that these functions are 1-to-1. So you should hopefully notice that this function here, this 2 to the x, passes both the vertical as well as the horizontal line tests, which tells us that an inverse does exist, which we'll talk about in the future. Okay, and so that's all the pieces. In terms of applications, there are things that we do with exponential functions. Here's an example of a place that it's used, which is investing money and coming out with some sort of, amount of money later. So this is just a formula, just, take a look there. I have it again up here, just so that you can see it while I'm working on this problem. So this is the amount that you have over time based on how much you invest, the rate that you're receiving on the investment. We have our N here, which is how many times per year the money's being compounded, as well as how many years it is being compounded for the T. So you can see that we need P, R, N, T if we want to answer a question like, how much money are we going to have over time? So what I want you to do, if you can, is please pause, see if you can fill in the correct values for P, R, N, and T into those places, and then come back and then we'll take a look at finding our answer. So in this case, P is our principal, that's 10,000, it's the amount that's being invested. Our rate is 4.3, we want to write that. We don't use the percent as a percent. Percentages are written as decimal, so I'm going to write that as a decimal. Dividing by 100, essentially, 4.3 divided by 100, which gives me 0.043. We have that it's compounded monthly. So that monthly indicates 12 times per year. So I'm going to put that. And we have for 4 years. So there we go. So we are trying to find A of 4, the amount after 4 years. So you're welcome to pause, see if you can plug those values into the correct spot, and then use your calculator and see what value comes out for you. All right, so I'm going to have 10,000 parenthesis 1 plus 0.043 divided by n, which is 12, raised to the 12 times 4. So you can do this in a couple steps. At this point, it really is just a plug and chug. So I'll just write that it should be 10,000 times. And then if you do that piece, you can put this into your calculator all at once, but it's 1.187312, 759, something, 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 you know, just keeps going and going. But we'll multiply that. And then we'll just round it thinking about money. So we have this. This would be to the nearest cent, as you can see, because we're talking about money here. So then I can write something like there would be 11,873.13 in the account after 4 years, if you want to add that. And, you know, so that's just all about the fact that you're investing, and over time and compounding, you're making more money. But it does use the idea of exponents. So that's why we are seeing it right here. But in the end, this is just, so far, just a plug and chug, put in the value, see what comes out. So the way to do this on a scientific calculator in one step is like this. And until I get myself an emulator for the computer, I'm going to be just using the fact that Desmos has a scientific calculator that I can use here on my computer. So I'm going to just, again, do this in one step. I'll put in the 10,000. The scientific calculators typically have a parenthesis. So I'm going to work to try to make this look exactly like what I wrote down in my setup. So I can put 1 plus, typically your scientific calculators will have the ability to make a fraction so that you can see what that looks like. I can put my rate here, and then in the denominator, I'm putting the number of times it gets compounded, and then I can put a parenthesis. My calculator also recognizes that there should be one there, which again is typical of scientific. I'm going to put my exponent here. It really depends on what kind of calculator you have, what you're going to see for that exponent. On my TI-30XS, I actually have a little, like it looks like a little up arrow. Sometimes I call it the caret, which is above the x squared button. And that will give me an exponent on this calculator. So there are a couple different things you might see. And then I have 12 times 4, which is 48. So I'm going to write the 48. And then as you'll notice with this Desmos calculator, it just goes ahead and gives you the answer over on the right-hand side as you're putting in your value. So we get the same thing that we got before, obviously, but this would be the way to put it in the calculator all at once and see your answer right away. So now we have transformations of exponential functions. So what you're seeing, the red function, not surprisingly, is going to be the f of x equals 2 to the x. So just be aware that that's what that basic function is. And now we're just transforming it. We've done this already. We just didn't do it with exponential functions, but I am here to tell you that you're going to see the same stuff that we've already seen in a past section, but just for this, function that we have here in red. So I guess what I'll do, since I made it red, good job for me, is I'll put it in a different color. So maybe I'll put our transformations here in green. So we want to remember from when we did this before that we have our parent function. The parent function is 2 to the x. So we know what that does. And then we just have minus 1. And just like when we did f of x equals x squared minus 1, it's the same transformation. And that's what we want to start seeing here is these patterns. So we want to remember that when we subtracted 1, we translated it vertically in the number of units, I should say, that we have after the 2 to the x. It's minus 1, so we're moving down. So it is transformed vertically, 1 unit down. Okay, so all we're going to do is take every single point that we have. I mean, not every single point because that would take forever, but some of our most obvious points or points that we can kind of recognize easily. And we're just going to move them down 1 unit. So we had the point 0, 1. We're going to move that to 0, 0. We have 1, 2. We'll move it to 1, 1. We have 2, 4. Now we'll have 2, 3. So notice every point is just going down 1 unit. That's all that's happening. We have negative 1, 1/2, so we'll move it down. Again, we're not so worried about what the actual points are, it's just that we're taking every point and moving it down 1. It's still going to have the same shape. That's what's really important about transformations, is just remembering that we have the same shape. We're just doing the best we can to create that same shape. Like I said, best we can, understanding that it should look the same, but everything is just 1 unit down. That's what we've tried to do here. That's the whole point. Okay, for the second one, we can rewrite that if you would, be helpful to you. There isn't really, okay, well, the only thing that I could do to kind of maybe help you see this a little bit better is I'm going to write it like this. So just x minus a negative 3. The only reason for doing that is to get you to kind of remind yourself that what's happening in the first one, the first example, was we were dealing with a situation where we had the parent function and then that minus 1 was after that. In this example, that 3 is occurring with the x. So it's the difference between, just taking you back a step, so it's the difference between, say, x1 minus 1 and then, or x squared minus 1, and x minus 1 squared. These are different transformations. One is happening vertically and one's happening horizontally, because one's happening after the parent function and one's happening inside the parent function. So hopefully you may remember that when something happens within the parent function, within where the x is there, that this is the horizontal shift, the opposite of what we are maybe thinking, because it's x minus a negative 3. So in this case, the transformation is a minus 3 that's happening. So it's a horizontal shift, horizontally, 3 units, and then that's going to be to the left. You can always think about this logically by saying, what value is going to give me that 0, 1? So we always have, as you can see, when you put in 0, you get 1. Now we'd have to put in a negative 3 right here to get that same 1. So negative 3 is now giving us that 1 value. So every point's going to be moving 3 units to the left. So we find any units we can and we move them 3 units to the left, and then we just connect them because it's a transformation. So I'm going to go back to green here, and then a 1 and a 2 and a 3, and a 1 and a 2 and a 3, and then a 1 and a 2 and a 3. And then, just enough to get the shape that we've already been talking about. 1, 2, 3 down here. And then we're just going to connect and send it up. And then send it here. There we go. So very similar, just with a different parent function, but transformations are the same. So a couple more of these, We've got negative 2 to the x, so this is a transformation as well. You can think of it as negative 1 times 2 to the x. That might give you a hint of what's happening because we're doing the 2 to the x and then multiplying it by negative 1. So it's taking every y value that you're getting once you plug in x, your y value, and then it's taking that y value and making it negative. Negative. Okay. So you're probably not surprised that it's a reflection by a reflection over the x-axis. So again, it's fairly straightforward, just a negative to every y value. So it's going to take every y value and just flip it. So 0, 1 becomes 0, negative 1. And we just want to be an equal distance from the x-axis. So we're here, and we're here, and we're here, you know, just enough, just enough. There we go. And connect and connect. So just examples of this basic exponential function, 2 to the x, which would work for any base that you have there, would be similar. And for the last one, so notice what's happening there is that the x is being changed. So the negative is within the x, not on the outside. And so this is also a reflection by a reflection, but not surprisingly, we're going to be over the y-axis. So we're affecting the x value. So notice when we put in, for example, when we put in 0, well, we still actually get the same value. So that's kind of exciting. So if I put in 0 for x, I'm still going to get 1. But if I put in a negative 1 for x, then that means I get 2 to the negative 1 or 2 to the 1. So that's a positive value. That's 2. So it's this reflection that's sending us over. All of our points are coming to the other side, equal distance of the y-axis. So we just go ahead and do those and just flip it around, and connect it. So it allows us to graph some exponential functions without having to do quite as much work as maybe we might normally have to do, simply because we can understand that it's just a transformation of that basic parent function, f of x equals 2 to the x. And that is section 4.1.